Okay, so hello and welcome everyone to week 6 of interactive live sessions for the course of Fundamentals of Convective Heat Transfer offered by NPTEL. The course is being instructed by Professor Amaresh Dalal from IIT Guwahati. I'm Debjit, I'm a TA of this course, and today we shall be solving problems related to convective heat transfer together. So, with no further ado, let's move on to question number 1 of today's session. So three statements are given. You are asked to consider the given statements and select which ones are right or wrong among them. So I'll read out the statement. Statement 1 says for Prandtl number approximately equal to 1, both velocity and thermal boundary layer develop at almost the same rate. For Prandtl number greater than 1, much greater than 1, the temperature boundary layer or the thermal boundary layer will develop at a slower rate than the velocity profile. And statement 3 says for Prandtl number much lesser than 1, the temperature boundary layer will develop more rapidly than the velocity profile. So among these three statements, pick out which ones are correct and then see if that particular combination is present within the options given below. So is it option A only 1 and 2 are correct? Option B only 1 is correct? Option C only 3 is correct? Or option D all of them 1, 2, 3 are correct?
All three are correct, sir.
Okay, so one response. Anyone else would like to respond?
All three are correct, sir.
All three are correct. Okay, let's have a look at the solution then. And indeed, all three are correct. So if we look at Prandtl number is nothing but the thermal diffusivity over the momentum diffusivity over the thermal diffusivity, and the growth of the boundary layers, they are proportional to these diffusivities. So the momentum diffusivity depends on this, and the thermal diffusivity depends on this. So if Prandtl number is almost of order 1, then both these velocity and sorry, this is a bad way of saying. Let's say the hydrodynamic boundary layer and the thermal boundary layer, they develop at almost the same rate. If Prandtl number is much greater than 1, that means momentum diffusivity is much higher than thermal diffusivity. Then the hydrodynamic boundary layer will develop at a much higher rate than the thermal boundary layer. So the in comparison, thermal boundary layer will develop at a slower rate. And the opposite case, where Prandtl number is much less than 1, then the thermal boundary layer will develop more rapidly than the hydrodynamic one. So it's a simple one. I hope things are clear. We will move on to question number 2. Question number 2 says for uniform wall temperature condition. Uniform wall temperature condition, that is, a temperature is constant. The value of Nusselt number for hydrodynamically and thermally developed flow in a circular pipe is how much?
3.66.
3.66. Okay, anyone else?
Yes, sir, it is 3.66.
Okay, so if we look at the correct solution, it is indeed 3.66. This was, I guess, taught in lecture 4 of week 6, where the derivation of the heat transfer within a circular pipe with uniform wall temperature, and the case considered was that the both hydrodynamically and thermally fully developed flow was flowing through the pipe. So in that case, there is a derivation using series solutions and so on. And finally, it boils down to the Nusselt number being a pure number, 3.66, which is independent of Reynolds number and Prandtl number, everything else. So this is you have to appreciate that this is a very powerful result which we can employ in multiple engineering and science solutions, where we know that if we have a fully developed flow within a circular pipe, then this would be the Nusselt number, and that could be directly related to the length of the pipe and not length of the pipe, any characteristic dimension. So this was, I guess, according to the diameter of the pipe, And if we know the thermal conductivity of the material flowing, the fluid material, then we can directly get H, or the convective heat transfer coefficient, and that helps us in calculating the rate of heat transfer. So for the other cases discussed also, we see that Nusselt number always, not always, but in these specific cases which were taught, Nusselt number actually boils down to pure numbers. So that's, I want you to appreciate how useful that result is. Okay.
Yes, yes, yes.
Moving on, we move on to question number 3 of today's session. So, question number 3 says the axial heat conduction in thermally fully developed laminar slug flow through parallel plate channel with uniform heat flux condition. There are many terminology here. So, it has to be thermally fully developed laminar slug flow through parallel plate channel and with uniform wall heat flux condition. In this case, what is the axial heat conduction? Is it option A 1? Is it option B 0? Is it option C varies linearly in axial direction? Or option D varies logarithmically in axial direction?
0, sir.
0, okay. One response is 0. Anyone else?
0, sir.
0. So if you look at the solution, indeed 0 is the correct solution. So why is it? Can anyone explain the reason why it is 0? Okay, so basically what we see in this case is that the dou t dou x, the derivative of temperature in the or the gradient of temperature in the axial direction, that is directly equal to dTm dx, where Tm is the bulk mean temperature, and this has a constant value. I hope I write this correctly. This was around Q P divided by m dot Cp.
Dot CP.
Am I correct?
Yes,
Yeah. So
yes,
this is
yes,
basically, the heat that is transferred within the within a fluid element being considered equal to m dot Cp dTm. So that's the change in thermal energy of that element of fluid. So that way, we know that dou T dou X is a constant value. So if we try to find out the actual heat conduction I will write this way. So this would be proportional to dou dou x of k t dou x, and k if we take constant, so this would be ultimately proportional to dou 2 t dou x2. And since we know that dou t dou x is a constant, the second derivative would actually boil down to 0, since a derivative
yes,
of a constant is 0. So that's why there would be no heat conduction axially, there would only be a radial component of heat transfer. Or in this case, perpendicular, not radial, in the perpendicular, the across the streamlines from the plate towards the direction of. Okay. All right. So moving on to question number 4, which says that for uniform heat flux condition, the value of Nusselt number for thermally fully developed laminar slug flow through parallel plate channel is how much? So here also the things to look at are slug flow, parallel plate channel, and thermally fully developed flow.
12, 12.
Well, any other guesses or not guesses, answers?
Yes, sir. 12.
12. Okay. The answer is indeed 12. So among the cases that we saw, that for slug flow means that Prandtl number is much less than 1. So Prandtl number is much less than 1. So therefore the development of hydrodynamic boundary layer is very slow compared to the rapid development of the thermal boundary layer. So the case which is considered is that there is thermally fully developed. The temperature profiles, they develop quickly, but the hydrodynamic boundary layer does not develop. Hence, there is a uniform velocity field. So u at any y location would be equal to um, which is the mean or the average velocity. So that kind of a uniform flow is called a slug flow or even a plug flow. So in that case, the value of Nusselt number is 12, which is one of the higher values. And why is that? Since there is a high velocity even near the walls, so those particles of fluid, they pick up heat quickly from the wall and then move away at a high velocity, and again brings in a cooler packet of liquid which will again take up it and move away. So that is why the rate of heat transfer is quite high. So you can imagine from a physical argument that means the convective heat transfer rate H would also be high, and as a result the Nusselt number would also be high. Does that make sense?
Yes.
Okay. So moving on, question number 5. Question number 5 says, in case of uniform wall heat flux boundary condition, with respect to uniform wall temperature condition, the increase in heat transfer for hydrodynamically and thermally fully developed flow through circular pipe is how much? So there are two conditions. One you have to consider for uniform wall heat flux, and the other is for uniform wall temperature, and you have to calculate the increase from in case of from wall temperature to from constant temperature to constant heat flux. What is the percentage increase in the rate of heat transfer? You can consider Nusselt number in case of instead of heat transfer over here.
Sir, it's 16 times.
16 times, okay. Any other answer? So see, one hint I'll drop. We saw in the previous example that, okay, so we will consider this as case 1 and this one as case 2. So we saw in a previous one that for uniform wall temperature in hydrodynamically and thermally fully developed flow, this Nusselt number becomes equal to 3.66, correct?
Yes.
And similarly, for if the heat flux was uniform throughout, then that would have been 4.36. So you can calculate the percentage change from this. And remember, it said that with respect to uniform wall temperature. So you have to consider that from uniform wall to uniform heat flux, if I go, what would be the percentage change? So simply writing this, the percentage change would be Nu1, which is the higher one or the increased one, minus Nu2. We take the difference. And since it said that with respect to the second one, so that's why divided by Nu2. And then you simply multiply it with 100%, some average value you will get. So if we
19% is the answer, I think.
90%, right? So if I take this difference and then divide it by 3.36 into 100%, should boil down to what? 19%. Is that right?
Yes.
Okay, so if you look at the solution, 19 is indeed the correct answer.
Debjit sir, I am
Yes.
having one query.
Yeah.
Uh, the same type of question is asked in the assignment, but I
See,
stuck there. No,
the
no, no.
material is same, so.
No, no, no.
Hmm.
Why I stuck there? Actually, I'm waiting for practice session only.
Okay.
And I actually want to ask the question related with it in query box, but they are not responding. That's why I'm waiting from your answer. Actually,
Okay.
what they have given in the assignment question, condition is not given. Circular pipe is not mentioned. Means probably they have mistaken. I think they have not mentioned circular pipe. They have not mentioned parallel plate channel, and only initial sentence is there.
Okay.
So, if you are going for a parallel plate, that percentage rise is something 8.5%.
Okay.
And if you are going by circular pipe, that percentage rise is
It's
19%.
19%. Yeah.
So, as the condition is not mentioned, it is not a parallel plate, not a flow through circular pipe. How I should means how we
Yeah.
should write the answer,
No,
because
it's
it
not.
is
It's not possible to write the answer. Like the sufficient data has to be given in the question. Otherwise, how will you write the answer?
no. It is actually typing answer, sir. It's not a selection.
Sorry, I didn't understand what.
It's box. In box we have to enter the value.
No, for that you need the sufficient data from the question, right? Whether it's a parallel plate case or a circular pipe case or something else.
Yes. That data is required.
That
Otherwise,
data
we
is
can't
required.
write it.
Hmm. So there are some issues in the questions posted, right?
Hmm.
Okay, I'll try to convey this to some of the NPTEL officials that I'm in contact with, but otherwise,
Because
really nothing is in my hand. So you can post
that's the
queries.
problem. Because what happened?
Hmm.
8 questions are there, and if we are losing one,
Hmm.
it's automatically 12% reduction.
Uh, that's that's correct. I understand that. So there is really not enough power in my hands as far as controlling those assignments are, but
Mhm.
I will try to convey this to some of the higher ups and let you know if there are any developments. Okay.
Yes. No.
So any questions regarding this one? This one was clear, right?
Yes. Fine.
So moving on, we will move on to question number 6, which is in the thermally and hydrodynamically fully developed flow of a fluid in a circular pipe with constant properties and uniform wall temperature condition, the wall heat flux varies linearly with axial direction. So the case given is the one with uniform wall temperature, and the question asked is whether the wall heat flux varies linearly or not.
Actually, sir, probably it is going on increasing,
Hmm.
but probably exponentially, not linearly.
Correct.
So it's false.
Okay. So if we have a look at the correct solution, it is indeed false. And your reasoning was correct as well. So if I remember correctly, then the temperature profile was something like this: T wall.
यस आपने
Uh,
ग्राफ निकाला था, एक ग्राफ
yeah.
में ऐसे एक कांस्टेंट था और एक इंक्रीजिंग था, तो
That
डिफरेंस
was
कम
for
होते
box
जा रहा था.
gas. Same thing can be told for internal flows as well. So
Mhm.
here the formula was e to the power minus something x. So with x it was decaying gradually, right? So the wall heat flux variation, which would be simply a derivative of this TWTX. So, and since this is a constant, the derivative of this would go to 0. And again, we will get some form of e to the power minus something x. There something would come here. So, we can see that this relationship, this variance of wall heat flux with axial direction, this is not uh, linear. It's a exponential one.
Exponential, and it is decreasing na because of minus sign.
Yeah, correct. So why is it decreasing? Like from a physical argument, you can say that if I have a pipe like this and the entire wall is at a constant temperature T equal to T naught, the fluid enters with some other T, let's say Ti, and along the x direction, if I plot this along x, if I plot this T, let's say this T naught is higher than the temperature of the fluid. So it's a hot pipe at a constant temperature, and there is a cool fluid coming in. So as it is flowing, heat is being transferred from the wall to the fluid. So the fluid is getting gradually hotter. This temperature difference is decreasing. But as you see, as this temperature decreases, this temperature difference decreases, the rate of heat transfer will also decrease. So this curves would the difference would gradually decay, and the rate of that decay would decrease with the difference itself. So and it would at infinity, at x equal to infinity, we can hope that this would actually become equal to T, which is the temperature of the pipe itself. So before that, it would approach that temperature. This is from purely from a physical argument, not a mathematical one.
Yes, yes, sir.
So moving on, we move on to question number 7 of today's session. Question number 7 is the temperature slope, uniform wall temperature at the wall is lower than the temperature slope for uniform heat flux, uniform wall
True,
heat flux.
true, sir. True.
So it is indeed true. Why is it so? So if we compare the temperature profiles of the two cases, uh, I will try to quickly draw two figures. So this one is for uniform heat flux, and this one is for uniform wall temperature. So here in the vicinity of the wall, the temperature profiles look kind of like this, and in between it, has a the curve reaches a minima and then again approaches and then again follows an exact symmetric curve. But in this case, where there is a q dot double prime equal to constant, there is a q over here. So the temperature profile would actually have a slope which is proportionate to this rate of heat transfer. And similarly, we would have a valley in between uh, where a minima would reside. So as you can see that the slope here is like this, and the slope here is not as steep as this condition. So if we look at the angles, this angle is much higher, this lower. This is a general case. In general. Okay.
Yes, sir. Yes.
Moving on, we move on to question number 8 of today's session. So, for a hydrodynamically and thermally developed flow through parallel plate channel, the decrease in heat transfer in case of uniform wall temperature in comparison to uniform heat flux taken with respect to uniform wall temperature is how much? So, this is similar to one of the previous problems which we did, and this you have to consider for parallel plate channel, and both hydrodynamically and thermally developed flow. So we have two cases, uniform wall temperature, we will consider this as 1, and uniform heat flux, we will consider this as 2, and we have to take it with respect to uniform wall temperature, that was 1. So basically if you find out the Nusselt numbers, then it would be, okay, we have to find out the decrease, right? So it would be Nu1 minus Nu2, so divided by Nu1.
Sir, answer is 8.43%.
8.43%. So help me out a little here. So Nusselt number for uniform wall temperature for a parallel plate. How much is that? Nu1
7.54.
7.54, and the other one Nu2
8.235.
it is
8.235.
8.235. I can take that as 235. So 8.24 I can take, right? Okay, so if we simply plug in these values, okay, I've made a mistake here. The decrease in heat transfer in case of uniform wall temperature 1. Okay, so 1 is lesser than 2. So the decrease is from nu2 minus nu1 and taken with respect to uniform wall temperature. So that one was 1. So this formula is correct. So we will have simply have to do 100%. Now, if I take the difference, uh,
Just a minute, sir.
yeah,
8.24 minus 7.54 with respect to बोला है Nasser number
wall
1.
temperature. So wall temperature was this 7.54,
It is 9.28%.
9.28%. So this would be the correct answer. Okay. So uh,
Actually, sir, but
yeah,
mm, in this, if you are saying a decrease,
hmm.
whenever we are calculating percentage decrease, actually it has to be with respect to higher value, sir. How they can give the answer with respect to
Yeah,
uniform wall
no,
temperature?
with respect to uniform wall temperature. So the base case that I'm considering is the uniform wall temperature. Now, in comparison to that, there are that case and another reference case. So we take the difference between them and then calculate it with respect to that initial one. Make sense? Or is it still ambiguous?
No, it's related with English grammar.
Yeah, English grammar, I
Whenever you
understand.
are saying decrease, na, that has to be
Yeah,
calculated with respect to
to
the
the higher one. So from the higher,
higher.
there has been a decrease. So
You
we
can
just
call it as a percentage change otherwise then.
so I can completely omit this part this with respect to whatever part. Then
Hmm.
if I pose this question in this way that find out the percentage decrease, then of course the default one would be the higher one.
Yes, yes.
You are correct.
Hmm.
This is a you know grammatical error, so to speak. Okay, so to that's all for questions of today. So if we try to summarize the Nusselt numbers for all the cases we have learned so far, because we see that those are the important ones. So what are the different conditions that we considered? So we considered slug flow plus thermally fully developed. So I'll write this as TFD, and we also considered both hydrodynamically fully developed as well as thermodynamically sorry, thermally fully developed. We considered two geometries. So those two geometries were parallel plates, and the other one was circular pipe. And when it comes to the thermal conditions, then there was this uniform. Sorry, there was this uniform heat flux condition, and there was this uniform wall temperature condition. For this, both fully developed conditions and the thermal flux or the heat flux equal to constant, that particular case was not considered. Other than that, all other combinations were done. So if we try to quickly summarize that, so we can say that let's say okay, so there are 6 cases in total. This is for TW equal to constant, and I can take and this is also for fully developed conditions. So for parallel plate, the Nusselt number there was how much? 4.36? No,
536.
7.
7.536.
And for circular pipe, this value was
4.36.
4.36. And on the other hand, if we take you know the and this is for the q equal to constant thing, again we have parallel plates in this column. We will write for circular pipes in this column, and for the slug flow case, this was 12 and this was 8, correct? With uniform heat flux, thermally fully developed flow. And when this was fully developed case, this value got reduced down to how much? 8.24 or 140 by 17. And in this case, the circular pipe and fully developed case, this Nusselt number reduced from 8 to 48 by 11, that is 4.36. So this summarizes the 6 cases which were considered in the lectures of week 6, and these Nusselt numbers are actually determinant of the heat flux conditions. And once again, I would reiterate something that I said earlier, that these are all pure numbers, totally independent of Reynolds number and the Prandtl number. Okay, so that's all for today's session. Any questions from your side? Okay, so if not, thank you all
Sir,
for
sir,
joining.
just actually,
Yeah.
sorry.
Oh, okay, sure. Please
Can
go
you go
ahead.
on the back side?
Yeah.
Yes, 7.54 and 4.36. Parallel plate and circular pipe. Okay, sir. Sir, one question is there.
Hmm.
Uh, if there is a flow through parallel plate or a circular pipe,
Hmm.
okay, properties are given to calculate Reynolds number and everything. Reynolds number, then Prandtl number, we can calculate. Then actually, at what particular point,
Hmm.
and the constant heat flux or constant wall temperature condition is given.
Hmm.
And at a particular point, if I want to calculate, the flow is fully developed. So that entrance length I need to calculate.
Yeah.
So actually, sir has given that formula.
Yeah.
Just
The entrance length formula, like there is a thermal entrance length as well as a hydrodynamic entrance length, and
yes,
I don't.
thermal entrance length something I'm having that LT by DH.
Okay, so I'll put DH here.
LT by DH hydraulic diameter.
Okay.
So for example, it is a parallel plate channel, it is 4H.
4H. Yeah.
4H, and for circular pipe it is D only. So LT by DH, CT, some constant is there, and Reynolds number based on hydraulic diameter into Prandtl number. So that is the formula.
That is the formula, right? Okay.
So this formula is applicable for constant wall heat flux or that too?
Uh, Okay, here basically there is the what the entrance length means is that there is a development of the boundary layer, and that would depend. Uh, no, so your question is what difference does it make if it's constant temperature or is it constant wall heat flux, right?
Okay. From the lectures,
Hmm.
we studied this formula, but I am not able to get whether it is for constant heat flux condition or constant wall temperature condition.
I'll look into it and let you know in the next class. But my guess right now is that would determine the value of the CT or the constant. The other part would be similar, like dependent on linearly dependent on Reynolds number and Prandtl number and hydraulic diameter. Only this constant would change.
Because in week 5 lecture, that CT constant, that table is there. But I am unable to recall that table. Probably in that table, that values are given. Number of values are there for CT and C. Just 1 minute.
If you hold on, I'll try to pull up the lecture slides from that. It was in week 5, you say, right?
Yes, this is week 5.
Week 5. Okay.
I will tell you lecture number also. Probably it is lecture 16, sir.
Lecture 16. Determination of heat transfer coefficient.
Mhm.
We will see. A table was given, no? A table.
Yes, yes.
I'm looking at the lecture slides which were shared. So for the 16th one, it was not there. Yeah, got it. Wait, I'll share this. So these were the lecture slides used by professor for taking the course, and here that particular table is given.
Hmm. Yes, yes,
So
yes.
as I said, the value of CT that is influenced by whether uniform heat flux condition is there or uniform surface flux condition is there. Other than that, the
Hmm.
form or the formula of the entrance length that remains the same, which is
Okay,
the
okay.
formula indicated on the top right corner. If you see LT by TH equal to CT into number into Reynolds number.
Yes, yes. So, if the question is like this,
Hmm.
for flow to be thermally fully developed, what should be the length of the pipe or channel?
Yeah. So for pipe, we can consider this geometry, the first case under geometry, where the geometry is that of a circular pipe, and we can use the value of CH as 0.56 and CT according to the thermal condition, whether heat flux or surface temperature is being held uniform, and then use accordingly whether 0.043 or 0.033.
No, that means what I need to understand here, for flow to be thermally fully developed, what should be the length of the channel? That means it is entrance length is asked, na? That is
Yeah,
another meaning.
minimum it should be entrance length. It could be more than
Mean.
that. So from the entry of that channel up until the entrance length, it would be a developing flow. After the entrance length, it would become fully developed.
So
So
here, expected thing is for flow to be thermally fully developed, what should be the length of the channel?
what
The
should be
meaning is
the
it is
minimum
entrance
length
length,
of the channel?
minimum length. That is expected.
Correct.
Yes, yes. Okay. Actually, I got miss that table. I am not recalling. I
Hmm.
have not written that table. Na? That's why
Okay, so
formula I know,
this
but
is the table. You can see the slide, right?
yes, yes. I will take the photograph of it. Yes,
No, this is actually available.
uh, yes.
After
Okay. Okay.
these lectures, there is a web page called lecture slides. Then you can see all the